Lecture 1A, Mathematics, Part 1. Concerning the mathematical tools that we'll be using this semester. The first of our tools is Pythagoras' theorem. You'll use it so often it'll be one of your best friends. Pythagoras' theorem deals with right triangles. A right triangle is a triangle where two of the sides are perpendicular at 90 degrees, or pi over 2. If our sides measure lengths of 3 meters, 4 meters, the long side of the hypotenuse would be 5 meters. This is known as a 3, 4, 5 right triangle. You will see many examples of 3, 4, 5 right triangles in this course. It doesn't have to be meters. It could be 3 kilometers, 4 kilometers, and 5 kilometers. It doesn't actually even be 3, 4, 5, as long as it has the ratio. It could be 30, 40, and 50. Same as saying a triangle of scaled up by a factor of 10. Or by a factor of 2, 6, 8, and 10, instead of 3, 4, and 5. Or by 3, 9, 12, and 15. How does this work? Pythagoras' theorem is a squared plus b squared is c squared, where a, b, and c are the lengths of the sides of the triangle. If we square the lengths, 3 squared plus 4 squared, that equals 5 squared. 3 squared is 9, 4 squared is 16, and 5 squared is 25. You'll see this works whether it's 30, 40, 50, or 9, 12, and 15, or whatever else that we use. That comes out to be the same ratio as 3, 4, 5. And it works for any type of Pythagoras' theorem works for any type of right triangle. But one of the most common right triangles you'll see, whether it's inclines of ramps or inclines that we use throughout the semester, such as ski slopes, or the vectors of velocity and acceleration and forces broken into its components or added together of various displacements or forces, you will commonly see 3, 4, 5 ratios of these vectors or these inclines. Another of your commonly used formula will be sohcahtoa. So in the sohcahtoa, the SOH is sine equals opposite over hypotenuse. Meaning we measure the length of the opposite to an angle, we measure the length of the long side of the right triangle hypotenuse, and the ratio of those lengths is what the sine of the angle is equal to. Cosine, or the ka in the sohcahtoa, is adjacent over the hypotenuse. The adjacent to the angle divided by the hypotenuse is equal to the function cosine theta. And the toa is tangent equals opposite over adjacent. The ratio of the sides that are perpendicular to each other is equal to the tangent of the function, the tangent of the angle. Some commonly used examples will be a 30, 60, 90 right triangle. Right triangles' interior angles add up to 180 degrees, so 30 plus 60 plus 90 equals 180. Again, you will see this often, whether it's inclines at 30 degrees from the horizontal, such as ski slopes and ramps and labs, or other examples in your homework, or vectors at 30 degrees to each other. They're there because sine of 30 and cosine of 60 are common functions. Let's see those. Well, if 30 degrees is the angle we're interested in, then the opposite length to the angle of 30, and we have a length that's adjacent to the angle of 30. Opposite divided by hypotenuse. If in a 30, 60, 90 triangle, if we measure the length of the opposite and divide it by the hypotenuse, we see that the length is equal to a ratio of 1 over 2. What that means is the hypotenuse is always twice as long as the opposite length, with the opposite length being the length that's opposite the 30-degree angle. But we know opposite over hypotenuse is equal to sine theta. So sine theta, when theta is equal to 30 degrees, is equal to 1/2, meaning the opposite, say the rise of the ramp or the rise of the ski slope, that's opposite of 30 degrees from the horizontal, is half the length of the slope, half the length of the hypotenuse. So you should memorize that sine 30 degrees is equal to 1/2. You will see this often in your homework, in your labs. Often things will be set up where the angle from a horizontal is at 30 degrees because sine 30 is an easy number to memorize, 1/2. The cosine of 60 degrees is the adjacent over the hypotenuse. Now we're talking about the adjacent to the 60-degree angle. So the length that we previously called opposite is now the length that's adjacent to the 60-degree angle. So adjacent over hypotenuse is cosine of 60 degrees. But we just saw that that length, whether we call it adjacent or opposite, is still half the length of the hypotenuse of the slope. So cosine of 60 degrees, therefore, must be 1/2. Again, cosine of 60 degrees is equal to 1/2, as is sine of 30 degrees. These will be something for you to memorize, as you'll see it often. It'll be used often to make us go through the math quicker and focus more on the concepts of physics. Well, if we know that whether we call it the opposite of 30 degrees or the adjacent to 60 degrees side is half the length of the hypotenuse, then what must be the third length, the third side of the triangle equal? Well, using Pythagoras' theorem, 1 squared plus that length squared equals hypotenuse squared. So let's rearrange our numbers here. Solving for that mysterious length, we get 2 squared, which is 4, minus 1 squared, which is 1. 4 minus 1 is 3, and therefore the length that's adjacent to the 30 degrees or opposite the 60 degrees is equal to root 3. So therefore, the cosine of 30 degrees must be root 3 over 2, adjacent over hypotenuse. And therefore the sine of 60 degrees must be also root 3 over 2, where the root 3 is now the length that's opposite the 60-degree angle. Here we see that cosine of 30 degrees is equal to root 3 over 2. Tangent theta, again, is opposite over adjacent. Now, when the opposite and the adjacent sides of a right triangle are equal to each other, the ratio of opposite over adjacent is equal to 1, that must be a right triangle where a length of one side, which we call A, is equal to the length of the other side, B. Therefore, the adjacent and the opposite are the same length. The ratio is equal to 1 in our right triangle. Well, what angle do we have here? Again, the interior angles add up to 180 degrees in a right triangle. So we know one of the angles, the perpendicular A and B, are perpendicular to each other. They're 90 degrees. So the two angles must add up to 90 degrees. And since the lengths are the same as A equals B, then the two angles must be 45 degrees. So this theta here and that theta there, those two thetas add up to 90 degrees, so theta must be 45 degrees. Therefore, tangent of 45 degrees is equal to 1. Next up, we'll see why the sine of 90 degrees is equal to 1. Well, sine of 89 degrees, let's think of what that means. Again, sine is opposite as a ratio of the length of the opposite of an angle that we're interested in divided by the longest side, the hypotenuse. So if the angle we're interested in is again measured from the horizontal, then the opposite to that angle of 89 degrees is almost the same length as the hypotenuse, as we see in the right triangle that's drawn for you. The opposite to the angle and the hypotenuse, those two lengths are about the same. The hypotenuse is about the same as the opposite. So sine of 89 degrees, which is the ratio of opposite over hypotenuse, is a ratio where the two sides are about equal, so the ratio is equal to almost 1. If we take this approximation to this extreme, where opposite and hypotenuse are the same lengths, because the angle is 90 degrees, then the sine of 90 must be 1. And the length of the adjacent side is disappeared, it's gone, it's 0. We can go the other direction. If our angle measured from the horizontal theta is small, then the hypotenuse and the adjacent lengths are approximately equal. And the smaller you get, the better this approximation is. The opposite side is getting small, and the adjacent side is getting longer, approaching the same length as the hypotenuse. So the cosine of this small angle is adjacent over hypotenuse, and it's approaching 1. Therefore, when theta goes towards 0, the ratio goes towards 1. As we can see, the hypotenuse and the adjacent sides are about the same, and when the angle is 0, the lengths are the same, and so cosine of 0 degrees equals 1. And the opposite does not exist. There is no length at 0. So if the opposite is equal to 0, then sine of 0 must be 0. And this concludes the functions of sine 30 and cosine 60 and the others listed that you should memorize for this course, as you will see them often. These functions are here to make your life easier by knowing these. These are some of the examples of sohcahtoa. We will use this quite often. It'll be one of your new best friends. This concludes part 1. Find the video for part 2 to explore the rest of the first chapter's mathematics that we need for this semester.